So ions part 2, dealing with electron configuration and Lewis dot structures of ions. So here we have potassium. We're going to draw the Bohr model for it, and you do need to add an extra ring. Potassium has 19 protons. It has a mass of 39. So you have 19 protons, and 39 minus 19 gives you 20 neutrons. So now we need to add our electrons, and our protons and electrons should equal since it's not an ion yet. Remember that the first ring can hold 2. The second ring we can have up to 8. The third ring we can have technically up to 18, but first you have your 8. And then in the fourth ring we're going to have 1. So we have 1 valence electron for potassium. Going to write its electron configuration. You should have gotten 1s2, 2s2, 2p6, three s2, 3p6, 4s1. So notice how our electron configuration and Bohr model go together. We have 2 in the first energy level. In the second energy level, we have 2 plus 6 is 8. In the third energy level, we have 8. And in the fourth energy level, we have 1. So we've got to think, is it going to gain or lose electrons? It's easier to lose 1 than to gain 7. When it loses, remember that it's going to have a positive charge. And since we've lost 1, it should have a positive 1 charge. Notice that it's going to lose the 4s1 because that's the outer electron. So if we're to write the electron configuration of the ion, we're going to write the exact same thing as before, except we're going to remove that 4s1. So now we have the electron configuration of the ion. If we were to draw the Lewis dot diagram, if we were to draw it of potassium, potassium would have 1 valence electron. But potassium ion, notice we've removed that outer electron, and so we do not have any valence electrons. So we're just going to have the box and a +1 charge. So we still have the fourth ring, it's just empty now. For carbon, you should get 6 protons for the atomic number. The mass is 12. So 12 minus 6 gives you 6 neutrons. And we have 6 electrons. So 2 in the first one and 4 in the second. You can look on the Bohr model and figure out that we should have gotten 4 valence electrons. And your electron configuration, 1s2, 2s2, 2p2. 2 in the first ring and then 4 in the second ring. Carbon's a little bit different because we have 4 electrons in the outer ring. It could just as easily lose 4 as gain 4. But if you recall that it's carbon, and carbon is a nonmetal, and nonmetals always gain electrons. So because carbon's a nonmetal, it's going to gain. And it should gain 4 because it's trying to satisfy the octet rule and have 8 in its outer ring. Remember that when it gains, it should have a negative charge. And it gained 4, or it should gain 4, and that's why it's going to be a negative 4. For the electron configuration of the ion, when we gain those 4 electrons, it's going to fill in that 2p. So instead of being 2p2, we're going to add 4 electrons to that, and it's going to become 2p6. For the Lewis dot diagram, carbon started with 4 valence electrons. So we draw carbon and add the 4 valence electrons. But it gained 4, so we need to add 4 more. That gives us a full outer shell, or 8 electrons altogether. So we have 4 dots, or 8 dots around carbon, and a negative 4 charge, representing our 2s and 2p. Go ahead and do the Bohr diagram, number of valence electrons, and electron configuration for argon. Restart the video when you have those 3 items. So for argon, looking on the periodic table, it has 18 protons and a mass of 40. So 18 protons and 22 neutrons. For our Bohr diagram, you should have had 2 in the first ring, 8 in the second ring, and 8 in the third ring. Which gives us 8 valence electrons. Your electron configuration should have been 1s2, 2s2, 2p6, 3s2, 3p6. So we have 8 valence electrons already, and the octet rule says that we want to have 8. So there's no need for this element to gain or lose. So it's going to do neither. So it's not going to form an ion. So you can ignore the other 3 questions. Remember that your noble gases have full outer shells, and so they don't participate in bonding. And so they don't make ions. Go ahead and do your Bohr model, valence electrons, and electron configuration for chlorine. Restart when you have your answer. So looking on the periodic table, chlorine has a mass, or atomic number of 17, mass of 35. So we get 17 protons, 18 neutrons. It has 2 in the first ring, 8 in the second ring, and 7 in the third ring. So we have 7 valence electrons, and our electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p5. So if it has 7 valence electrons, is it easier to lose 7 or gain 1? If you said gain 1, you are correct. If it gains, remember it's going to have a negative charge because electrons are negative, and we gained 1, so that's a -1. It's going to put that 1 extra electron in the 3p so we can fill up that 3p. And so it's going to become 3p6 at the end. Anytime you gain electrons, you have to have as many dots as the atom, which was 7, and then you just add as many as it gained, in this case 1. Make sure you have brackets and the charge on the outside. So anytime it's negative, add electrons. Anytime it's positive, then you're going to subtract electrons or erase them. Okay, so looking at your groups and families, remember that group 1A always has 1 valence electron. So group 1A is always going to lose 1 electron. And so everything in group 1A, which is the alkali metals, should have a +1 charge when it makes an ion. You have 2 valence electrons in the alkaline earth, and so they're also going to lose 2 electrons, giving everything in group 2A a +2 charge. In the middle, silver, you need to write in as a +1. Zinc and cadmium are +2s, and aluminum is a +3. Group 18 is your noble gases. And remember, noble gases have 8 valence electrons, so they don't have a charge. Your halogens have 7 valence electrons, and that's only the nonmetals. And so that gives it a -1 charge. Group 16, the nonmetals in group 16 have a -2 charge because they have 6 valence electrons. Group 15, the nonmetals in that group have 5 valence electrons, so they're going to have a -3 charge. And carbon and silicon will have a charge of -4. And boron is an odd one with a +3 charge. So notice the metals that you know the charge of. Group 1A, 2A, silver, zinc, cadmium, aluminum. Remember in the last video we said those were the ones that did not need to have Roman numerals. All your other metals do need Roman numerals. And that's because their charges can change. So all the yellow ones I just highlighted are variable charges. Variable meaning that they change. You can have multiple charges. Because of that, you have to use Roman numerals when you name them. Just an example, lead can be a +2 or a +4. So that's why we need Roman numerals to distinguish if it's the +2 or +4 ion. So here we're going to figure out what the charge of each element is after it gains or loses electrons. So calcium, if we look back, calcium is an alkaline earth metal, so it should have a +2 charge. So that's what you're going to do for these. Go ahead and pause the video and figure out what the charge of each of these should be when they gain or lose electrons. So nitrogen was a -3, potassium a +1, bromine a -1, oxygen a -2, magnesium a +2, aluminum a +3, and cadmium, you should have got a +2. You can tell that because nitrogen's in the -3 column, potassium's an alkali metal, so +1, bromine is a halogen, so -1, oxygen's in group 16, magnesium is an alkaline earth, aluminum is a +3, and cadmium is a +2. Alright, so let's do one of these together. We're going to be writing the electron configuration of the ion and the Lewis structure for the ion. So the first thing you have to remember is the charge that aluminum has, and that's a +3 when it's in its ion form. The easiest thing to do is to write the electron configuration of the atom first. So aluminum has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p1. But if it's a +3 charge, then that means it loses 3 electrons. And so it loses the 3p and the 3s because it has to lose it from the outer shell. So my electron configuration is just 1s2, 2s2, 2p6. Aluminum would have had 3 valence electrons, but we lost those 3 valence electrons. And so no dots, just a +3 charge. Go ahead and pause the video and try the next one on your own. So oxide ion is oxygen, and oxygen has a -2 charge. So I write my electron configuration, but since it's a -2 charge, then that means I'm going to gain 2 electrons, and I would gain them in the 2p. So that's going to become 2p6. Remember that when you gain them, we have to write how many we started with, which was 6, and then we gain 2. So that gives us a total of 8 valence electrons now. 2 in the S and 6 in the P. And it has a -2 charge. Go ahead and do the next one on your own. Restart when you have silver done. So remember that silver was a +1. Write its electron configuration out. And again, it's a +1 charge. Silver's a little tricky, as are all the transition metals, because notice that the highest number, which is its outer electrons, is in the 5s. That's why all the transition metals always have 2 valence electrons, because you fill the s and then you go to the d's, which are in a lower energy level. So it's got to lose it from the outer ring, which is the 5th one, and so that turns into 5s1. When you're drawing Lewis dot structures, it's always of the outer electrons, which in this case is the 5th energy level. Notice I have 1 left in the 5th energy level, and so it's going to have 1 dot. Don't forget your brackets and charge. So silver originally had 2, but we lost 1. Finally, try lead. Restart when you have lead. And go ahead and do lead the shorthand configuration. So we have xenon, and then 6s2, 4f14, 5d10, and 6p2. Notice that my outer energy level is the 6s2 and the 6p2 because those are the higher numbers. So if I lose 2, I'm going to lose it from the p first because that was the last one to fill. And so that turns into 6p0, or you can just erase that. So although lead had 4 valence electrons, now it only has 2. So that's what it did look like. Now that's my Lewis dot structure. But don't forget your charge. And again, it still has 2 because it still has the 2 and the 6s.